Hello, in this video I will show you how to calculate Phonon dispersion curves using universal machine learning interatomic potentials and how to visualize the results in an interactive online website application. Specifically, I will use maze potential and the uMLIP-Interactive interface, and I will show you two options. Either I can directly calculate the Phonon dispersion curves in this interface, or I can prepare a standalone Python script that will go through each structure file in my folder and it will calculate the phonons. Okay, so first of all you need to have compiled and installed this app, and you can get it from my GitHub. The link is here, and I will also put it into the description of this video. And in the documentation you can find the details how to obtain it and install it. And also I prepared previously some tutorials about how to use this interface for some other calculation types. So I will suppose you have this and directly show you how to use it for the phonons. So first of all I need to upload these crystal structure files, and I prepared them here. So I will show you alpha titanium, beta titanium, and the one perovskite. And let's say or let's use now this alpha and beta titanium in this interface, and then all three with the standalone Python script. So I will just upload the structure files here, click accept and lock it, and then here I have to specify which universal potential to use. So I will use maze MH1. The calculations I will perform with the GPU because it's much faster. And yeah, that's it. And then I will select here Phonon calculation task, and I can modify some parameters, but for the simplicity let's keep it as it is now. And I can either use automatically determined high symmetry k-path, or I can determine it or set it myself. So let's use the same one for both crystals. And I can also it will automatically perform geometry optimization before it will calculate the phonons, and like this is optional. If you already have the optimized structure, you can just uncheck it. I will keep it on now. So that's all for the settings, and now I can go to start calculations and start batch calculation. In the calculation console I can observe like how it's running, but this is very fast. So yeah, now it's done. And so I can go to results and phonons, and I can see the calculated dispersion curves and the corresponding density of states. This is for alpha titanium. If I switch to beta titanium, I will see negative frequencies, which is expected because this phase is stable at 0 temperature. Okay, and to visualize these like phonons, or how the atoms move at each phonon frequency and mode, I can download. If I go down here, I can download this band YAML file. So if you click and download it, I already have it here in the results saved for alpha titanium. And then I can go to this great website which allows me to visualize the phonons. And I will choose here the file, or also I will put the link into the description of the video, and I will choose file and select this YAML, and you can see it loaded the structure and loaded the Phonon curves. And if I click on some mode, I can observe how the atoms are basically vibrating. Yeah. Okay, so that's one option how to compute the Phonon dispersion curves in this interface, and the other option is to prepare a standalone script. And for that I will again go to Start Calculations, and I will click here Generate Python script. So this will automatically read either POSCAR structure formats or a CIF format in my folder, and for each it will calculate this task type. So I will just copy the content of this script, go to my console where I want to start the run, and okay, so I will go to with script, and here I have these three crystal structure files, and I will create the script to run, insert the content, save this, Ctrl S, exit, Ctrl X, and now I can simply run it. Simply run this standalone Python script, but before that I had to activate my virtual Python environment where I compiled all the necessary packages. For that, like how to do it, you can also find in the documentation on the GitHub. So let's run it. Okay, and this will not take much time and will be quickly done because the structures are small. And okay, so it finished, so I can see the results. And if I go here, for each structure there is a separated folder, and in each folder you can see the calculated Phonon curves and the corresponding density of states, and also this YAML file which you can upload into this interface and observe how the atoms are moving in each mode. Okay, so to see just the barium titanate, so this is also and this phase is also seems unstable at the 0 temperature, and yeah, but still I can upload the output files here, and I can observe how the atoms moving. Okay. Yeah. Yeah, so that's all how to calculate the phonons with universal machine learning interatomic potential and the uMLIP-Interactive interface. And I hope you will find this useful, and thank you for your attention.